Morning everybody, welcome to physics today. So we finally get to start in on two-dimensional motion. So that's what we're going to be talking about today. And we will be using everything we learned from one-dimensional motion, but we'll just use it in two dimensions. So the first thing that we want to talk about is the whole idea of vectors. So you guys know how to do vectors now, right? So let's look at this. If I have a vector like that, could I define that vector as this plus this plus this plus this plus that?
No.
Yes, I could, right? Because it starts here and it ends here. So I can do anything I want to vectors as long as I start and stop in the same spot as the original vector. And if you remember our first lab too, everybody did different addition of the same vectors and got to the same place and it was equal to the same thing, right? So order doesn't matter, we can put in extra vectors. But the reason why we did all that is so we can manipulate the vector into whatever works for us mathematically. So for example, if we have a ramp, okay, so when Galileo studied gravity, he wasn't able to study it as it's falling off the Leaning Tower of Pisa. How come? Anyone know why? Yeah, so the reason why I didn't drop things off of big buildings is because there was no video to take pictures and, stop frames to get good data points. There's no real good, timing device for something that takes less than a second. So it was impossible to actually study gravity by just dropping things. So what he did is he diluted gravity. So he'd have a ramp, and he looked at how the changing angles changed the acceleration down the ramp. And then with that, he was able to determine what the acceleration due to gravity would be straight up and down. So today we're just going to look at the relationship. But if I have a ball here, and I'm ignoring rotational inertia, which is the amount of energy that it takes to move mass, we'll talk about that later too, but if I have a ball, do we know what the acceleration, or do we know what the force of gravity is on that ball? Or which direction at least? It's straight down, do you agree? The force of gravity on anything is always on a radius of the Earth. So it's completely perpendicular to the tangent of the Earth. It's straight down. Does that make sense? Okay, so it doesn't matter what's in the way. The force of gravity is always towards the center of mass. Okay, so we have this vector. Now, now if I was going to put acceleration due to gravity, what would this number be? Well, we'll say 10. For all of our calculations, we'll use 10. You can use 9.8 if you want, but 10 is the way to go because of the less calculations and more physics that we concentrate on. It is truly around 9.8 depending on where you're at. But we'll use 10. So, could we split this vector into something that's more useful for us? The answer is yes. Tell me how or what. One thing you always have to remember when you're doing vectors and you're going to be splitting up actual value, whatever the real value is, like in this case 10 meters per second, that's always the hypotenuse. So you can't add to that vector. So when you're going to make a right triangle first of all, right? Because we're studying right triangle trigonometry, SOHCAHTOA. That's what we did for the last 4 or 5 days. So we need to make a right triangle with that being the hypotenuse, because I can't add to that vector. And I really only have 2 legs to put in there because it's a right triangle. Andrew. So Andrew said that it would be beneficial to have a vector or part of the vector that's perpendicular to the ramp. Okay? So that's part of the triangle. What would the other part of the triangle be? What's the one that's really useful for us? Because where's the ball going to accelerate? In the direction of the ramp, right? So the one that's really useful to us is this one that is parallel to the ramp. Okay, so now we have our little right triangle here. This piece is the right angle, the acceleration due to gravity is the hypotenuse. Now, this is a good triangle, but now we need to relate that triangle to this triangle, and we need to figure out what this angle is, because this is something that we can measure, that angle, or this is something that's given. So how do we relate these two triangles? And more specifically, which angle is related to that angle in the triangle? Okay, I'll let you think about that for a second. I'll have kids come up to do that. Geometric proof. Yes, that's exactly right, Andrew. And what he said is, this right here is a right angle. This here is also a right angle. This is a right angle, which means on the other side of that line is a right angle too. Okay, and Andrew said that since this is a 90-degree triangle, this is complementary to this angle, and this angle then is complementary to that angle. So that's the most simple geometric proof showing, or proving even, mathematically, that this angle theta is equal to this angle theta. Okay, very good. So with all that said, then, we can use our SOHCAHTOA, because this part of our acceleration due to gravity is the part of the acceleration that's in the direction of the ramp, which then becomes the acceleration down the ramp. So, which trigonometry function do we use to figure out that side? So, yes, so sine is opposite over hypotenuse. This is opposite, right? So the sine of theta is equal to the acceleration down the ramp times the hypotenuse. In this case, then, the acceleration down the ramp is sine theta hypotenuse. Acceleration down the ramp is, I'm going to give this angle now, 30 degrees, is the sine of 30 times 10 is 5 meters per second squared. And that's now our acceleration down the ramp. Okay, so what do you do with that? Well, you want to figure out how fast it's going at the bottom of the ramp. Because eventually what's going to happen is we're going to have conservative or energy conservative energy. We're not going to lose any energy later when we make this transition from the velocity in this direction to this direction. And we're going to have it fly off the table. So we need to know what the velocity is at the bottom of the ramp. Okay, so let's say that this ramp then is a distance of 3 meters. My question then is going to be, what's my velocity at the bottom of the ramp? That'll be my final velocity, right? So I could use this formula v squared equals v sub naught squared plus 2ax. And as far as new formulas, there are none. We still have just the 3 kinematic formulas that we've been working with. So the velocity at the bottom of the ramp is going to be equal to the square root of 2ax as long as my initial velocity is 0. Okay, so in this case, it's equal to 2 times 5 times 3 meters is the displacement that occurs down the ramp. My so my velocity then is equal to the square root of 30. And I am going to ask you to probably put that in decimal form when you do it. So now we know that our velocity here at the bottom of the ramp is 30 meters per second. Or I mean the square root of 30 meters per second. Okay, any questions about that? Okay, so the next part of this is talking about what happens in the x and the y direction during projectile motion. So projectile motion is considered free fall motion, which when there's only one force on the object, and that force is gravity. Okay, so let's say that we have a velocity in the x direction of 5 meters per second. Okay, so this is all x's, right? Is there a velocity in the y direction? No, there isn't. Now, once this goes off the edge of the table, will there be a velocity in the y direction? Yeah, the instant after, it's going to start going towards the center of the Earth with an acceleration rate of 10 meters per second squared. So the whole thing about the x and the y stuff is they are completely independent. Okay, so that's the hardest thing for you guys to get, because your whole life you've seen them acting on the same object. So if I throw something, you can see that the x and the y velocities are combined as one vector at all times throughout the throw. But the thing is that x has no acceleration as long as we're in free fall, which means there's no air. And the y has acceleration due to gravity. So we have to make sure that we do the math with the x and the y stuff independently, because the force is only in the y direction, which will only change the y characteristics. Okay. So what's going to happen here is I'm going to have a certain amount of time to fall. So remember that little lab that we did when you figured out how long it took to fall from the chair, and then you figured out how long it took to fall from your hand, and then you got to stand on the table and figure out how long it took to fall. Do you remember that? Or maybe you timed it. I'm not exactly sure what the lab was. I forgot about that. But what did we know as we went up in height? What happened? We had more what? We had more time to accelerate. Right? So we had more time to accelerate and more time to fall. So this is where it gets a little funny. This right here is not going to change throughout the fall at all. But if we're talking about how far away from the edge of the cliff we're going to go, then we're talking about the velocity in the x direction times the time described by how long it takes to fall. So, when we do this problem right here, what we need to do is figure out how long it takes to fall with the y stuff, and then we can plug it into our formula, and we'll figure out how far away from the edge of the cliff it lies. So, what we need to do then is figure out how long it takes to fall 15 meters. Okay? Because that's how much time. Like, for instance, let's just look. If I was going at 5 meters per second from here, it'd probably fall like that, right? If I was going 5 meters per second here, it'd fall like this. And from here, it's going to finally fall that far. It all depends on how much time I get to go in the x direction. So, how do you figure that out? Well, let's see. Keeping in mind, when you do your math, you can only do x stuff or y stuff. You can never do xy stuff. So if you're all x's and all y's, you're all good. If you're not, you're not. There's some graphing ways to do some of this together, but it only goes so far. So, I'm going to talk about the y stuff right here. Okay, so on my variable list, I have my displacement is negative 15, my acceleration due to gravity is negative 10, my time is what I'm looking for, my v sub naught in the y direction is 0, my v in the y, I don't know at this point. I'm looking for time. So I look at all my formulas, and I notice I can use this one right here. X equals v sub naught t plus 1/2 at squared. And that one's so nice because I don't have an initial velocity, so I cancel that out. So then x equals 1/2 at squared, which I heard this was on the math section of the junior test last week. Or time equals the square root of 2x over little g. Okay? You won't get that formula for the test, but by the time this chapter is over, you'll probably have it memorized. Just keep in mind it comes from here. Okay? So to actually find the time then, my time for this ball is equal to the square root of 30 over 10. My time is equal to the square root of 3. Okay? Any questions about that? So the question was, are we just solving for y? That is, now we either just solve for y or x independently. Because these things they have to be treated independent because there's y acceleration happening, there's no x acceleration. And even if there was, they'd be different, so you still treat them independently. So, in this case, I forgot to tell you this, there's a special way to spell time now, and it's like this. Time. And the reason why that is because how high you are, or whatever's happening in the y direction, is usually what determines how much time you have to do your x stuff. So that's kind of why we did that lab where we kept going higher and higher, and you could tell that there's different times happening. So keep this in mind that you spell time. Now, that doesn't always happen. Like you might have a variable where you're hitting a wall or something before the y can, culminate. So the question was, is this velocity here x or y? And the answer was, you can only have a checklist for either x or y stuff. You can't intermingle them. So this is a y displacement, or vertical, you might call it. This is a vertical quality. So this has to be a vertical quality because it's in the same checklist. I have to erase the y part of that. Now, so, in the textbook, they might use y for this instead of x. But to me, that seems a little more confusing, more variables to work with. But you can do whatever you want as long as you are doing this correctly. So the one thing that the x and the y absolutely share is they're acting on the same object, and time is the one thing they share, right? So we use the y stuff a lot of times to find how much time the x stuff gets to act. So in this case, I'm just going to jot time up here as the square root of 3, and then I'm going to show you how to take care of the x, which the x is very easy. We'll look at a checklist this first time, but I'll probably never do it again. The x is what we're looking for. The velocity in the x direction initially is 5 in that direction. The velocity final in the x direction is 5. Because there's no force to accelerate that in the x direction. The displacement is what we're looking for. The time that it gets to happen is the square root of 3. The acceleration is 0. Oh, I guess I did displacement twice. Okay, so with that checklist, then, we can use the formula, and really what the formula is x equals v sub naught t plus 1/2 at squared. But this time, we have no acceleration. So that cancels out. X then equals velocity in the x direction, which is the initial and the final since there's no acceleration, times time that it gets to fall off the cliff. So x equals 5 times the square root of 3. And that is our displacement and how far away we are from the edge of the cliff. Questions?